Hi, my name is Harrison Butker, and today I will be analyzing the motion of a football being snapped as part of Lab 5, Choose Your Own Adventure. I first filmed the football being snapped and then documented the various X and Y coordinates of the football along its path. I then decided to try and figure out the velocity of the football when the ball had left the snapper's hands, the final velocity of the football when caught, and also the force applied by the snapper on the football. My results indicate that the initial velocity of the ball when it is released from the snapper's hands was the vector negative 20.2, 2.94, 0 meters per second. The final velocity of the football when caught was the vector negative 16, 1.18, 0 meters per second. The force applied by the snapper on the football is the vector negative 136.4, 17.15, 0 newtons. To begin, here's what the motion of the football being snapped looks like. Here's the VPython model of the ball being snapped. When making this motion on VPython, I imported the X and Y data points from Tracker, and then I created a while loop that subtracted the various X coordinates and Y coordinates and found the velocities, and then plugged that into the momentum principle, which I will continue to talk about later. If you want to pause the video, you can. To find the initial velocity of the ball, I divided the change in time by the change in position between the data point where the ball is no longer touching the snapper's fingers and the point where the ball is still in contact with the snapper. I found this velocity to be the vector negative 20.2, 2.94, 0 meters per second, which amounts to 20.41 meters per second, which is also 45.56 miles per hour. Finding the final velocity of the ball was fairly similar, and then I divided the change in time by the change in position of the last two data points and found the final velocity to be the vector negative 16.1, 1.18, 0, which is 16.04 meters per second, and that amounts to a speed of 35.88 miles per hour. To find the force applied by the snapper on the ball took a little more time. To find this value, I used the momentum principle that states the final momentum is equal to the initial momentum times F net times delta t. This can be simplified to show that the change in momentum over the change in time is equal to F net. To find the change in momentum, I found the velocity when the snapper was no longer in contact with the ball and when the snapper was in contact with the ball. I then subtracted these values from one another and multiplied this value by the mass of the football. This gave me a net force vector of 136.4, 13.27, 0 newtons. After I found F net, I knew that the force of gravity, the force of drag, and the force of the snapper were the three forces acting on the ball, and since the time interval was only 0.033 seconds, I could neglect the drag force. The equation for the force of gravity is mass times g, with g being equal to 9.8 meters per second squared, and m being equal to 0.396 kilograms. So now I just have one unknown force and can find that by saying that the force applied on the ball by the snapper is equal to F net minus the force of gravity. This value is a vector of 136.4, 17.15, 0 newtons. Our first question states, is air resistance present in this motion? And the answer is yes, air resistance is present because the velocity of the ball when it is caught is 16.04 meters per second, and when it is released from the snapper's hands, it is moving at a speed of 20.41 meters per second. This means that if no one was there to catch the ball would continue to slow down due to air resistance. The second question states, why is the motion jagged and not smooth? Well, an American football is not a sphere, but a prolate spheroid that looks like this. Since this object has pointed ends, the air is going to either get under it and push it upwards or get over it and push it downwards. In this video, the snap was not a perfect spiral, so the air in turn was pushing the ball upwards and downwards throughout the entire route. If the snap was a perfect spiral, or if the object was a sphere, the motion would look more like this, instead of the jagged route. Thank you.